Okay, let's dive into this. Today we're exploring the absolute cutting edge of clean energy by unraveling the microscopic world of organometallic halide perovskite solar materials. I know, it's quite a mouthful, but unpacking this microscopic world reveals exactly why scientists around the globe are so hyper-focused on these crystals right now. We're going to look at what happens inside them the very millisecond that sunlight hits their surface, and why a bizarre micromystery inside their atomic structure holds the ultimate key to the future of our power grid. Now, to really grasp the stakes here, we have to talk about one specific number, 27.3%. That is the massive, freshly updated power conversion efficiency benchmark for perovskite solar cells. Just to put that into perspective, a little over a decade ago, these materials were barely scratching 10%. The speed at which they've improved is literally a massive leap in photovoltaics. But as we push higher and higher, brushing right up against the theoretical limits of physics, we start running into these stubborn, performance-limiting roadblocks. To protect that 27.3% and, push it even higher, we can't just rely on trial and error anymore. We have to become atomic detectives. We need to know precisely what the atoms inside these materials are doing when they absorb light. Now, what's really interesting about this is when we zoom all the way in to look directly at the suspects in our micro-mystery, we see the classic ABX3 crystalline lattice of a perovskite. You can see the inorganic cage-like structure that's made of lead and iodide ions. But look right in the center of those cages. Those are our ace-site cations. On one side, we have methylammonium, or Ma, and on the other, formidinium, or Fa. At first glance, this crystal looks like a static, rigid scaffolding, but that couldn't be further from the truth. When a photon of light crashes into this lattice, it doesn't just knock an electron loose to create electricity, it actually triggers a physical, vibrating response. The whole environment literally shifts. And that brings us to the core concept of our explainer today, the photo-induced Stark effect. You can kind of think of the Stark effect as a sort of internal electric breeze. When light hits the solar cell, it generates an electric field that perturbs or disturbs the local atomic lattice. This perturbation actually causes spectral changes, meaning it shifts how the material absorbs light. Because the crystal structure itself is slightly bending and warping under the sudden internal electric breeze, its optical signature changes. It's a subtle clue, sure, but a massive one, because it proves that the generation of electricity in these materials is inextricably linked to actual physical movement at the atomic level.
So how do you actually see this invisible breeze? Well, researchers turned to a brilliant technique called photo-induced absorption spectroscopy. By shining different wavelengths of light onto the perovskite film and measuring the exact optical changes, scientists can map out this Stark effect in real time. They're essentially tracking how the local electric fields inside the crystal change dynamically. It's almost like taking a high-speed X-ray video of the atoms responding to light. And what they found using this technique was honestly incredibly surprising. They realized that the crystal doesn't just react to light in general. It reacts very differently depending on the exact color of the light hitting it.
Let's break down those clues by comparing red light and blue light. Red light, at 630 nanometers, carries lower energy. It excites the electrons, sure, but the resulting structural shift is mostly temporary and relatively minor. But blue light at 470 nanometers packs a much higher energy punch. When a blue photon hits the perovskite, it doesn't just excite an electron. It provides what we call excess thermalization energy. Think of it as a massive thermal kick. And researchers discovered that this specific kick from blue light provides exactly the energy needed to overcome the activation barrier for ion diffusion. In plain English, blue light actually gives the ions inside the crystal the power they need to physically break away and migrate through the material. And this brilliantly illustrates the macro-level consequence of that blue light kick. If you look at photovoltage decay, it shows us that if you illuminate the solar cell with red light and then turn it off, the voltage drops off relatively quickly. But if you illuminate it with blue light, the voltage decay is significantly slower. It really drags out in a long tail. Why is that? Well, because that excess energy from the blue light caused so many ions to physically migrate out of position that it created a literal atomic traffic jam. The material fundamentally reorganized itself, and it takes a lot longer for the system to relax back into its original state. This is wild because it proves that light isn't just making electricity, it's actively moving the physical building blocks of the solar cell around. So the crucial point is, how do we actually control this? How do we stop our solar cells from rearranging themselves every single time the sun shines? The answer lies in those ace-site cations we looked at earlier. Comparing these specific cations tells a really clear story. Methylammonium, or Ma, has a very strong dipole moment of 2.22 dBs. It basically acts like a heavy magnetic anchor. Its strong dipole shields the electric field and locks the surrounding iodide ions in place, which leads to very low diffusivity. But then look at cesium. Cesium is just a sphere with zero dipole moment. Without that dipole anchor, the diffusivity of the iodide ions absolutely skyrockets. They move hundreds of times faster.
By combining all these clues, researchers mapped out the exact atomic domino effect triggered by light, and it happens in 3 distinct steps. Step 1. Light hits, causing an immediate charge transfer that physically changes the length of the lead iodide bonds, which tilts those rigid cages. Step 2. Because the cage tilted, the delicate hydrogen bonds connecting the cage to the organic A-site cation inside suddenly shift. And then step 3, the organic cation, reacting to this totally new environment, violently rotates or flips. If it doesn't have a strong enough dipole to anchor things down, this rotation physically knocks an iodide ion out of its spot, causing displacement. So 1 photon of light, 3 steps, and suddenly your crystal is degrading.
Let's move to and see how this builds visually. You can almost feel the mechanical stress building up as the inorganic octahedrons tilt on one side of the structure. Then, that thermalization energy from the blue light gives the iodide ion that final push to break free and move, completely coupled with the rotation of the methylammonium molecule. It is an incredibly dynamic and honestly chaotic environment in there. When you imagine billions of these events happening across a commercial solar array, you can start to see why solving this micro-mystery is absolutely crucial. So what does this microscopic atomic dance actually mean for us in the real world? Well, it causes local electric field changes that lead to something called anomalous current voltage hysteresis. Basically, the solar cell performs differently depending on whether the voltage is going up or down. The ions migrating through the material create internal roadblocks for the electrons trying to get out. It creates major inefficiencies. The cell literally gets tired because its internal structure is migrating. This hysteresis is without a doubt one of the single biggest roadblocks limiting the long-term performance and commercial stability of perovskite solar cells today. Which brings us right to the core thesis of this entire explainer, pulled straight from the research. We know that a mechanistic description of these processes is crucial for understanding and suppressing performance-limiting effects. Simply put, we cannot fix what we don't understand. By using the Stark effect to prove exactly how light, heat, and dipole strength dictate ion movement, we finally have the instruction manual. We know that to suppress these performance-limiting effects, we need to carefully engineer the chemical mixture of those A-site cations, balancing things like Ma, Fa, and cesium to create an anchor strong enough to withstand the thermal kick of blue light. And that leaves us with a truly exciting prospect. We're already hitting 27.3% efficiency while still battling these microscopic ionic traffic jams. So just think about it for a second. If we take this exact mechanistic understanding, if we can successfully engineer the perfect A-site cation cocktail to lock every single ion permanently in place under the blazing sun, what is the true efficiency limit of tomorrow's clean energy? Could we hit 30%, 35%? The blueprint is finally right in front of us, and the future of solar is looking brighter and for sure far more stable than ever before.